जिनिवाते दीनाम् अवित्रवतो.
So, good afternoon all of you. Now you already done organic chemistry, physical chemistry in detail. Let us talk something about analytical chemistry. It is a little bit and very basic topic we will be discussing. So, as you can see, it is a quantitative analysis and introduction to analytical chemistry. Now, you have been studying chemistry for last maybe 3-4 years. And when you study chemistry, basically we divide chemistry into 3 major branches: physical chemistry, then organic chemistry, and analytical chemistry. Now, before we begin, what is analytical chemistry? Let me ask you a simple question. We have been studying these 3 branches. So, let us start with the first. What is chemistry? What we study in chemistry? Well, answer can be very enormous, very big, but to condense it in the smallest form, we can say that chemistry is a study of matter and its various transformations. When you say matter, what is matter? Matter is everything around us, including us also. And when we study matter in detail, we find that it is composed of different substances, then elements, molecules, and atoms. Right? So, chemistry is basically study of all these different compounds, how they are prepared, how they are synthesized, why we convert from one form to another, and then their fundamental nature like molecules and atoms. So, that is basically what we study in chemistry. And for other convenience, we have branched it into 3 major branches, as you can see, classical branches: physical, organic, and inorganic. So, what we do in physical chemistry? Yes? Well, physical chemistry is a theoretical study of chemistry. It gives you a theoretical understanding or basis why reactions happen, if they are happening, what is the rate at which they happen, if at all reaction is possible or not. All these questions are answered by physical chemistry. In thermodynamics and in kinetics, we study these aspects. Then comes inorganic chemistry. So, what is inorganic chemistry? Yes? Study of elements. It is basically a study of elements. How many elements are there naturally occurring? 92. Starting with hydrogen groups, uranium 92, and plus 10-15 or what man has prepared in the laboratory. So, all these elements presently 118 up to 118. So, study of all these elements, their properties, structures, various compounds obtained by combination of these elements, all these aspects we study in inorganic chemistry. And then last, the favorite, organic chemistry. So, what we do in organic chemistry? What is organic chemistry? It is study of carbon and its compounds. Now, always a question comes in my mind: why entire branch has to be devoted to a single compound? Yeah. What might be the reason? See, only carbon and entire big branch of chemistry is to carbon. So what? Why is it so? Yes, the first property is catenation. Carbon has got catenation property, catalytic property. And second is that being a tetravalent, and it is found in all living systems. And that's why it is a very important branch of chemistry, organic chemistry. So, initially chemistry was this: physical, inorganic, and organic. Then came analytical chemistry. So, is it a new branch of chemistry, analytical chemistry? No. Why? It is a part of chemistry. Or which part of chemistry? It is part of physical chemistry. How can you say it is a part of physical chemistry? It is part of all chemistry. Basically, analytical chemistry started as a chemical analysis. All of us are aware of chemical analysis, isn't it? In the lab, we do practicals. So we do chemical analysis. So analytical chemistry started as a chemical analysis, but remember, it is not restricted only to chemical analysis. It is much more than that. And therefore, towards the end of last century, they have given a separate name as a analytical chemistry. So there was a separate branch as analytical chemistry where we will be studying, I definitely will be studying with different methods of analysis, but again, there are not many things which we study in analytical chemistry. We will see how to go about analytical chemistry. Okay, so what analytical chemistry is? It is a chemical characterization of matter. And if you want to define analytical chemistry in a simplest terms, analytical chemistry is a science which deals with identification, isolation, and estimation of each and every constituent present in the given sample. So first part comes identification. Now when we want to identify something, we need to do some chemical test. So first you identify what is the given sample. Then what you do? You isolate that by employing different separation methods, starting with simple distillation, product extraction, chromatography, and so many. And then lastly, you find out how much of that particular constituent is present in your given sample by a different method. So that is what we call as identification, isolation, and estimation of each and every constituent present in the given sample. So that's how analytical chemistry was defined. So it is basically a chemical characterization of matter. So when you do analytical chemistry, why you do it, or basically what it is concerned with, it gives answer to 4 basic questions. That is, what is there? Where means in sample where it is located, how much, the basic question, and lately what arrangement is there, what is structural arrangement of that particular constituent. So these 4 points or 4 parameters for any given sample are studied under analytical chemistry. Now of course, when you start doing analysis, the first question you always ask is what is there. Now when you ask what is there and when you investigate what is there, you are basically doing quantitative analysis. Isn't it? You are doing quantitative analysis. And then when you, after you know what is there, you seek to identify how much is there, how much a given sample is present, or how much a given particular metal ion is present in a given solution. So that aspect is called as quantitative analysis. So analytical chemistry basically it is a chemical analysis, started as a chemical analysis, and when you talk about chemical analysis, always you have 2 aspects. One is qualitative analysis, other one is quantitative analysis. So as we have this step, qualitative analysis is what is present, and quantitative analysis is how much is present. Now, we talk about real sample. So far in the lab, you are doing so many practicals, right? Qualitative analysis, volumetry, gravimetry, so many things. Remember, all these are pre-conditioned samples. What do you mean by pre-conditioned? Sample is already prepared in the form of solution or powder or whatever it is. That you take up, either dissolve it or dilute it, and then that's it. Remember, this is a very small part of actual analysis of a real sample. So what do you mean by real sample? Yes? To an analytical chemist, a real sample is anything and everything under the sun is a real sample. Okay, suppose you are working as a chemist in some clinical laboratory. Then, so blood sample is your sample which will be a real sample. So you are working in a forensic lab. So a dead fish is your sample, real sample. So these are the varieties of different samples which we constitute when we do analytical chemistry. So real sample is anything and everything under the sun. For example, soil or its pH, forensic sample, agricultural sample, and so many are there. So that is what you do actually when you go for a job in the industry as an analytical chemist in a QC or R&D or anywhere. Now we have discussed real sample. What are the real samples or what can be a real sample? Now let us discuss, as we have defined in our analytical chemistry, let us discuss what is the scope. What is the scope of analytical chemistry? Why we need or why we want entire separate branch as analytical chemistry when we have three classical branches, doesn't it? So the answer lies in it has got enormous scope. Pure or combination. That is why we have devoted a separate branch of chemistry to analytical chemistry. So what is the scope of chemistry? Analytical chemistry, it is applied everywhere. Whenever you are doing any chemical analysis, remember you are doing analytical chemistry. Whenever you want to answer question like what is there and how much is there, you are doing analytical chemistry. So the scope is enormous. In a single word we can say it is enormous, but still we can have some raw areas where it is applied extensively. So what are those areas? First is fundamental research, then quality control and quality assurance, assay, environmental pollution and environmental pollution control and monitoring, and clinical and biological testing. These are the few areas where analytical chemistry is used extensively. Let us go first, fundamental research. What do you mean by, of course, fundamental as well as applied research, both. What do you mean by research, basically? Yes? Research, right? Putting on new light on something which already is going, or doing it another way, finding some new aspects about it is basically a research. Here we are talking research, not invention. Invention is something different, something very new is invention. But basically research is throwing a light upon a known fact in a different way to gain some extra knowledge about that particular thing. Now when you do research, maybe fundamental or applied, in any kind of at least chemical research, you are always confronted with these two questions, right? What is there and how it is there. So again, when we say what is there and how much is there, analytical chemistry does, right? So we are talking about analytical chemistry. Second is quality control and quality assurance. These are the terms which we often deal with when we are working in the pharmaceutical industry or maybe in any chemical industry. But there is a certain difference between them, quality control and quality assurance. Anybody knows what is the certain difference between quality control and quality assurance? Yes? Remember, quality control is the analysis or routine analysis done on a finished product of that particular manufacturing unit to maintain the quality of that product. The test what quality control chemist does, they are prescribed by higher authorities. So here the quality chemist will only do the test as per the protocol. He has got SOP of that particular test. He will analyze the sample according to SOP. If the sample fits in his prescribed limits, say purity from 95% to 100%. If sample fits in that, it is okay. If sample is not fitting in that, it is not okay. So what kind of people does this? They will analyze the sample according to the guidelines given to them. Who sets the guidelines? Quality assurance. Quality assurance people will set the guidelines. What is the nature of sample? They have to study extensively. What is the nature of sample? What is the raw material used for it, manufacturing it? What should be the purity of that sample? If it goes less, what should be done? If it becomes more, what should be the control measures? All these aspects are studied and decided by quality assurance, and then they draft the SOPs. How to analyze that sample routinely in a testing laboratory. Because in the manufacturing unit, when you go to industry, for example, the drug industry, they will manufacture 10,000 tablets per day. So it is impossible to analyze 10,000 tablets per day. So they will be given to QC lab in a batches. First batch, second batch, third batch, and then analyze small lot from each batch as per the prescribed guidelines. If it matches with if the results fit in those formats or those limits, sample is okay, batch is okay. And remember, it is always very simple to work in a QC lab to analyze the sample routinely, but it is very difficult to go in QA lab and to do the decision making. There is one more aspect. As long as everything is going smoothly, no problem. Everybody is happy. Right? Normal shifts are going on. When problem comes when you want to reject a sample. Remember, rejecting sample is very difficult, because when you reject a single sample in a QC lab, you are rejecting a batch of 10,000 tablets. And in industry, it has got commercial implications. Because ultimately, industries are going to sell those products to the market, to the customer. And when you are rejecting it, you have to be damn sure. You have to be very sure why you are rejecting. Remember it very well. Because after a few years, you will be doing that job. So rejecting the sample is very critical. Anyway, so this is what we do in quality control and quality assurance. Now third comes assay. What do you mean by assay? Yes? Estimation. Okay. Estimation is half the answer. What is assay? Let's take example of paracetamol. Everybody knows paracetamol? Yes. Which drug is there in paracetamol? Yeah? Which active drug is there? It is paracetamol. Okay. So what is there? Active ingredient. Aspirin. Acetylsalicylic acid. Is the active ingredient in that. Remember, in paracetamol tablet, your active ingredient is aspirin. Along with that, what it contains? That tablet has got beautiful white color. So it has got titanium oxide as a coloring agent. It has got different shelf life. It is written on the label, no expiry date. That shelf life is written what? Because in that tablet there are some stabilizers are added, which gives that definite shelf life to that tablet. Right? So your crocin tablet contains it contains aspirin or acetylsalicylic acid. Along with that, it contains coloring agents, stabilizing agents, binders, adders if it is say fluid sample like ointment or So this sample contains everything. When you analyze such a sample only for its active ingredient, then it becomes assay. Assay is estimation of only active ingredient from the sample. So when you analyze your crocin or only content of active ingredient, that is aspirin, that is called as assay. You are not concerned with how much adder is there, how much binder is there, how much coloring agent is there. You are not concerned with that. That is what you are doing, assay. Okay. So in analytical chemistry, routinely in the biochemical analysis, you do assay of tablets. tablets or ointments or creams or whatever it is. In that you find out how much is active ingredient and how you do this. There is a prescribed method. Who decides that method? Ultimately analytical chemist. So it is a job of analytical chemist to set up a method. And method should be accurate, reproducible, cheap, non-interfering. It should not interfere with all other ingredients which are there in that sample. Okay, that is one. Then environmental pollution control and monitoring. Again, the same example of fish. A fish is, you got a dead fish from a Thane lake, and somebody told you it has died from mercury poisoning. So that fish becomes your sample, and you analyze that fish to find out how much mercury is present in that fish. Remember, the amount of mercury present will be in ppm range. Okay, so here again, environmental pollution controls. To control the environmental pollution, how much pollution or what is the limit for pollution? Now we see always the charts. This say chlorine should not be more than this ppm. Arsenic should be less than this amount. Who decides that amount? And how do you decide this? You decide it by testing the effects of arsenic on living systems, and then you set a limit. So everywhere you do a testing. So for environmental pollution control, whatever guidelines or whatever limits that are being set, that are devised by analysis of the samples, and therefore analytical chemistry plays a vital or a major role in that. And of course, monitoring. For monitoring of pollution or extent of pollution, you also again rely on different analytical methods. And then clinical and biological testing. In all clinical laboratories, nowadays, even if there is a fever, doctor first tell you to go and blood test. So always you need to go to a clinical lab, give your blood sample, and then the chemist will analyze those. So in clinical and biological testing also, analytical chemistry plays a major role. And of course, when you talk about analysis, again there are so many fields where analysis is of prime importance. So, lastly the question remains, does analytical chemistry means only chemical analysis? No. One, remember, chemical analysis forms a major part of analytical chemistry, but analytical chemistry doesn't mean only chemical analysis. Okay, analytical chemistry, what is the job of analytical chemist? Or what do analytical chemists do? No doubt they do the routine analysis, definitely. But it is the job of every analytical chemist to modify the method if necessary. Now, why one needs to modify the method? Always in the industry, we will want a better method which is more accurate, more selective, more specific, and more cheaper. Because ultimately in the industry, everything is related to profit. Okay, so it is a continuous, operation or continuous work is going on to update the existing methods. How we can make the methods better. So it is a main concern of analytical chemistry. One more thing, as we are moving with the modern times, every day we are confronting with modern samples, new samples. And how to analyze those samples, nobody knows. So it is again a job of analytical chemists to devise new methods to analyze new samples. And it is much more important thing. So analytical chemistry mainly concerns with chemical analysis and development of existing method or devising a new method for chemical analysis. And of course, seeking for betterment of existing methods, technologies, and everything. Now let us go to the classification of chemical methods, because we will be mostly concerned with chemical analysis part of analytical chemistry. Yet we are not concerned with how to modify your method. First, we need to learn all the methods, and then we think of modification. So let us see how various analysis methods are classified. There are various ways of classification. The first way is, I think they have, yeah, okay. They are classified in three ways. The first is based on information obtained. What information you are getting from the analysis of the sample? Based on that, you have different types of methods. The first is partial analysis. What do you mean by partial analysis? As the name itself suggests, partial analysis is you analyze the sample partial. So there are 3-4 different constituents, you analyze only 1 or 2 constituents. That is partial analysis. Then proximate analysis. Now in proximate analysis, what do? You analyze the given sample to find out only elemental composition of that sample. What are the elements present in that sample and maybe how much they are present. You are not concerned with how they are arranged in that sample. You are not concerned with molecular arrangement or structural arrangement of that sample. You are only concerned with elemental composition of the sample. So that is called as proximate analysis. Now, trace analysis. What is trace analysis? Trace analysis is a part of partial analysis where you are finding out a particular constituent which is present in very small amount or trace amount. For example, just now we were discussing the example of fish sample which has been contaminated by mercury pollution. Remember, your fish sample weighs in few grams, maybe 10 grams, 50 grams, whatever it is. And amount of mercury which you are finding out is ppm range, micrograms. So this becomes a trace analysis. Okay? And then, of course, complete analysis. What do you mean by complete analysis? You analyze the given sample completely and find out each and every constituent present in the given sample. That is what is called as complete analysis. Now, this is the one classification. The other classification is based on sample size. Macro, semi-macro, and micro. These are the 3 main types. Of course, there are so many types. But let us start with macro. What do you mean by macro analysis? When the sample size is more than 100 milligrams. When sample size you are analyzing is more than 100 milligrams, it is called as macro analysis. Semi-macro, your favorite, you do of it, right? Semi-macro is when the sample size is between 10 to 100 milligrams. Is semi-macro. And remember how much time sample you take. This much. Sample size between 10 to 100 milligrams. That is semi-macro analysis. And then micro. What is micro analysis? Sample size less than 10 milligrams up to 1 milligram. 1 to 10 milligram is micro analysis. There is also what as sub-micro. What is sub-micro? Sample size between 0.1 milligram to 1 milligram is sub-micro. And then micro trace. Sample size less than 0.1 milligram up to 0.001 milligram. It is called as micro trace analysis. Okay, for our purpose, we remember only these 3: macro, semi-macro, and micro analysis. And the last classification is based on various physico-chemical principles. See, all these chemical analysis methods are based on various physico-chemical principles. Then, for example, if you take identity, on what principle it is based? Yes? It is based on a reversible reaction, or it is based on a stoichiometric reaction. You have one component X, you add another component Y, both react stoichiometrically. When reaction is complete, that completion of reaction is indicated by your indicator. And then you find out how much amount of X is required to react specific amount of Y so that you find out the exact concentration of Y. That is what you do in titrating or titration or molecular analysis. So every method, every chemical analysis method is based on certain physico-chemical principles, and based on this there are large number of methods. So we see their classification. So these physico-chemical principles are broadly classified as, first is of course, first very broad classification is classical methods and instrumental methods. Let us talk about classical methods. What do you mean by classical methods? Old methods. So classical methods are gravimetry and volumetry, which we do. So what is gravimetry? Yes?
Measurement of mass.
Measurement of mass. Or gravimetry is a method, is a quantitative method of analysis where you find out concentration of given sample by measurement of mass. This gravimetry. Again, you classify into two types. One is direct, one is indirect. Indirect means what you used to do it in FIDs. You have a mixture, you heat it, golden part evaporates, subtract from 100 to find out indirectly the amount of other component. That is indirect gravimetry. And what you do in direct gravimetry? You have given a solution. You convert it into a precipitate. Isn't it? You filter it, dry it, weigh it, and from the weight you find out amount of particular item or particular constituent given the solution. That is direct gravimetry. Then volumetry also. Direct volumetry, acid, base, phenol, direct titration or direct volumetry. Indirect volumetry, sometimes you analyze the gas involved or pack titration. You do pack titration of PDT, right? That is indirect pack titration method. So these are two classical and still used today methods. Remember, they are not outdated. They are very much in use. Regarding gravimetry, all of us know gravimetry is a very slow method, very elaborate. There are so many steps you need to do. Filtration, washing, titration, so many things. And there are so many, that method is prone to so many mistakes. If you don't do it this way, then this will happen. If you don't do it this way, this will happen. If you don't filter it gradually, then precipitate tends to get contaminated. If you don't wash it with electrolyte, precipitate again contaminates, or your precipitate may dissolve and goes along with the solution. There are so many things. So, but still remember, even though it is very elaborate, accuracy is not very high. You get answers up to very high, but still it is routinely used in industry. Don't feel that gravimetry is not used. It is used, very much used in industry. Okay? And volumetry, of course, everybody uses it. Starting with simple titrations to auto titrators. We have volumetry up to auto titration, but still, physical data is the same. It is volumetric analysis. Then talk about instrumental methods. Now, when you talk of instrumental methods, you have a Pandora's box, whole variety of methods, and then they based on various interaction of the sample with the matter. That is what instrumental methods are. Let us classify them briefly. First is optical methods. What are the optical methods? Optical methods are those methods which depend on interaction of the sample with light. Those are optical methods. The basic principle is interaction of the sample with light. Now, what kind of interactions are possible? I have a sample, suppose, and I focus light on it. What things may happen? There can be absorption of light. There can be reflection of light. There can be scattering of light. Right? There can be transmission of light passing through without happening anything. There can be rotation of light. Specific rotation, right? So, based on each and every phenomena, you have number of methods. Let us first take absorbance. I have a sample, I focus light has got absorbed. So what which methods generally come to our mind when we talk absorbance methods? UV visible. We are the first. UV visible spectroscopy. Aya. NMR again it is the absorbance method. NMR. Yes. AS. Atomic absorption spectroscopy. All these are absorption methods, and each will give you different information. Okay, when you do UV visible, you will get electronic structure of that particular sample. You are also able to find the concentration by calibration flow method. If you have the series of standards and unknown sample, your Lambert's law. If you are using IR, you get structural information, different types of bonds, stretching, vibrating, seesawing. Then if you are doing the NMR, you get different sort of information. In AS, you get it deals with the atomic species, atomic absorption spectroscopy. So you get different information. Quantitative analysis. So these are different methods available in absorbance mode only. Let us go to emission. Emission of light. In emission mode, which methods are there? Not many. Basic method you start with flame photometer. You irradiate the sample and it is kept in the flame. Some atoms absorb the energy, go to higher state, they come back to ground state, emitting the excess of energy in the form of characteristic light, and what we measure. And from that we do quantitative analysis. Qualitative as well as quantitative. Which wavelength is emitted gives you what is the sample, and how much is emitted gives you how much is the sample. That is flame photometer. Same principle is used in AES, ICP AES, atomic emission spectroscopy, ICP, interchangeable plasma atomic emission spectroscopy. What is there? Only the flame is replaced by ICP torch. Principle remains the same. Sample is excited, goes to higher state, comes back to ground state, emit a characteristic light. Then, so these are two basic emission methods: flame photometry, ICP AES, then fluorescence and phosphorescence. Again, these are two emission methods. Fluorescence, some definite samples, definite structures you can reduce from fluorescence analysis. Phosphorescence, delayed fluorescence. So again, these are emission methods. Then go to the third type of interaction, that is scattering. Scattering of light. You have two major methods: calorimetry and calorimetry. Right? Calorimetry and calorimetry based on Laplace effect. The sample interacts with the boroidal suspension. You do calorimetry or calorimetry where you will do the quantitative analysis. And then lastly, the rotation methods. Which methods are there in rotation? You can find out alpha, that is specific optical rotation. Theta is optical rotation, alpha is specific optical rotation. By knowing alpha, you can do qualitative analysis. And by measuring theta, you can do quantitative analysis. Already you have series of sample solutions. So both can be done using rotation methods as well. So only optical methods gives you these many choices. Let us go to electroanalytical methods. Now electroanalytical methods are based on interaction of electrical parameters with the sample. Interaction of electrical parameters with the sample. Now what are the electrical parameters that are there which we can study with the sample? First parameter is potential, interaction of potential with the sample. So this gives us potentiometer. Okay. Then interaction of current or changing current with the sample. Current means change in potential and change in current. That gives you voltammetry, polar cyclic voltammetry, so many different methods. Then comes conductance. Change in conductance of the sample due to conductometric calculations. Okay. You also make use of conductance in your physical methods. By no specific conductance. right? Equivalent conductance and infinite dilation, lambda is great. Those values you can do, and that has its own use in your chemical analysis. Then comes quantity of current. How much quantity of current is utilized by the sample? How much quantity of current flows to sample for how much for reference period of time? That gives you coulometric titrations and coulometric titrations. So these are again very specific and very accurate quantitative methods of analysis, which you study by interaction of change in current for definite time with the sample, right? So these are your electroanalytical methods. Next comes thermal methods. What are thermal methods? It is interaction of the sample with change in temperature. The first and basic method is thermogravity. TGA. What you do in TGA?
Keep the sample and get it simultaneously.
Heat the sample and weigh it simultaneously. You study and you subject the sample to continuously rise in temperature and see how structural changes occurring in the sample, how its weight reduces. Classic example of calcium oxalate. That thermogravity curve. That is what we do in thermogravity, which will tell us what is the composition of sample at each every step of temperature and how much it is stable. Then comes DTA. What is DTA? Differential thermal analysis. What do you do in DTA? You keep the sample and reference in the identical conditions, and then you subject them both to the same change in temperature or same rank, and see how structural changes are occurring in sample as well as your reference material. Then we have DSC. What is DSC? Differential scanning calorie method. Where again you find out, you subject the sample continuous run and you study how heat changes or what is the amount of enthalpy changes taking place in the sample using a calorimeter. Differential scanning calorimeter. So again, this method is highly specific and accurate for particular type of analysis. Then comes radioanalytical methods. What are radioanalytical methods? Based on interaction of radioactive samples or radioactive samples with the matter. For example, NAA, neutron activation analysis. What do you do in neutron activation analysis? You irradiate the sample classically by thermal neutron, induce the activity in that sample, and study its structure and composition and of course concentration. That is what you do in neutron activation analysis. Then carbon-14 dating. You find out the age of old specimens, the wood or old living systems by the carbon-14 dating. So it is a radioanalytical method. Then of course these are methods of analysis. Then we come to chromatography. Chromatography itself is a huge. There are so many chromatographic methods available to analyze the given sample. Now the job in chromatography is dual. First it will separate and then it will identify each one. So isolation and estimation is done simultaneously in chromatography. It starts with the classical method like vapor chromatography, thin layer chromatography, column chromatography, gas chromatography, HPLC, hydrocarbons liquid chromatography, ion chromatography, HPTLC, then SFC, supercritical fluid chromatography. Now they have UPLC, ultra high performance liquid chromatography, and is continuously improved. Right? Yes? And GCMS, ZCMS, like that. So chromatography gives you host of different methods to work on. Then comes, I think, of course, along with this, there are some miscellaneous methods as well. For example, classical methods like of separation, because separation is again one of the critical aspects of analytical chemistry. Many times, before analyzing a sample, you need to separate. So, starting with a simple distillation, filtration, distillation, fractional distillation, solvent extraction, chromatography, electrophoresis. So many methods are also available to separate the result constituent and then to analyze by individual methods. That is not there. So these are the different methods available for analysis. Now, how to select the appropriate method? You have nearly 1000 methods, or 1000, but at 100, up to 100 methods at our disposal. Now, it is our job as analytical chemists how to select appropriate method for appropriate analysis. Okay, that part we will discuss in next. Thank you.